We have started recording, so we can start the session. Kristan, are you there?
Yes, I'm here.
Okay, great. So it's a pleasure to have Kristan, who will be talking about quantum world with Szegedy and Lindbladians, a lot of interesting things. Please.
Thank you very much, Boguslav. So first of all, to the organizer, I'd really like to thank you for inviting me and giving the chance to speak here. And so what I'll be talking about is some joint work with Pavel Wojcian, who's also a co-worker of mine at IBM. And what we've been thinking about is a particular family of quantum walk-based algorithms, and they're sort of called Segety walks. There's some way of, they're meant to originally basically take a particular classical kind of walk and attribute a unitary quantum walk to that classical kind of walk with very special nice properties, which I will try explaining out in a bit. What we try to do in this work is basically, okay, if that works for classical random walks, how about taking actually quantum processes and quantum maps and trying to see whether there's some way of associating a Segety type unitary to Lindbladian and having a quantum walk based on that, which is a purely unitary quantum walk, essentially. And so this is what this talk is going to be about. And it's meant to, in the end, be sort of a blueprint for quantum algorithms, okay? And just for the outline, what I'll try to do is basically, I shall give a really brief refresher of quantum computing, so what we want to do, certain things. And before I basically discuss our results, I'd actually like to spend some time on explaining Segety walk unitaries for classical Markov processes in a little bit more detail, because a lot of those properties are going to show up in our case as well. And lastly, I'm just going to show you what our construction is to end up with these Segety walk unitaries for particular classes of Lindbladians. Okay, so I'll give a very three-slide refresher of quantum computing. I hope no one is offended by that, because it's extremely elemental. Let's start with that. So what's a quantum computer? Well, a quantum computer a priori is just a quantum system that you have classical control over. So you can get classical data input. You can send certain signals, microwave signals if you like, and that are being processed in the quantum device. The classic, and you get to measure sort of single qubit measurements and get classical bit strings as output. And so these little square, this is actually a 7-qubit quantum chip, a very noisy one, a very small one. And what you can see there are these little rectangles. They're essentially trans-1 qubits, and you can think of them as being just effectively spins, having a Hilbert space of C2. They couple to each other through some interaction. In our case, that's a cross-resonance gate. And the Hilbert space you're working with is essentially just the tensor product of all these individual spin systems, i.e. tensor product of C2 to the tensor power n for n qubits. And so if you think about everything that we'll talk about now, it's basically just the Hilbert space dimension, capital N, say, it's just going to be 2 to the small n, and everything is finite dimensional. Everything's are just matrix algebras, and that's where we work in. And so what's the goal? The goal is to basically come up with a quantum algorithm on this device. And so what does that do is basically, we tend to depict that in terms of these quantum circuits, and that's essentially just a way of drawing matrix multiplication. So multiplication of unitary matrices, so every individual tensor component gets a line, time flows from left to right. And whenever you draw a box there, that sort of corresponds to a unitary operation that acts on either a single qubit or 2 qubits, potentially more qubits. Other things you get to do is you get to measure individual qubits, indicated by these pink boxes, and reset them and keep on going. And the entire task in terms of coming up with the quantum algorithm is finding a gate sequence that basically does what you want it to do, including with measurements, so that you can in principle implement whatever it is that you seek to implement. So that's all that you care about in doing it in terms of a quantum algorithm. And what you have to do that is physically you have to find some way of implementing a elementary set of gates that basically end up being universal. So there's if you have one 2-qubit gate called that C0 gate, which is incidentally induced by that Hamiltonian that I showed you earlier, and then you have like a single qubit S rotation, a single qubit Hadamard rotation that gets you the full Clifford group of n qubits. And if you then augment that with one gate of every qubit, which is called a T gate, you end up with a universal set of quantum gates, and you can span an epsilon net, approximate any unitary you like in terms of only these 4 gates and products thereof. Okay. So there's one particular quantum algorithm that we're going to be using quite a bit, and that's the quantum phase estimation algorithm. And a simple explanation of what that does is it's effectively just a tool for us to measure complicated observables. And from a physics perspective, all that it does is actually just the simulation of a von Neumann measurement. Right, so you basically have one system where you define an observable, call it H, say if you want to measure the energy with the Hamiltonian, and there's a joint tensor register called the pointer register. And now if you jointly evolve with e to the IH tensor P and have that unitary evolution on, say, a state that is where the pointer register is essentially at 0, and you happen to be in an eigenstate of that observable, what you can see is basically what that unitary evolution does is, so since momentum generates translations from the intuition, it just basically pushes the pointer registers to the energy value times t. And so that procedure is roughly called phase estimation. And so just that's the intuition behind that. Effectively, what you have to do is you have to implement a particular kind of unitary circuit, where sort of the top row are a bunch of it corresponds to discretization of the phase register. The bottom row is sort of the register of the physical evolution, and you basically have to evolve for powers of 2 essentially to push that discretized pointer register ahead. And then in some sense of an approximation, you're effectively simulating a discrete version of a von Neumann measurement that I explained before. And what it does is basically it copies it tangles the eigenbasis of some observable that you want to measure, or the eigenbasis of the unitary with the pointer register. And if you now basically measure, if you were to measure the pointer register and you were to collapse, you would induce, you would learn a measured value of energy, and you would collapse to a particular eigenstate. So this is what that routine essentially does. And we'll need that quite a few times. This is why I described that in a bit more detail now. Okay, so before we dive into our contributions, let me review basically what Segety walk unitaries are. So that's something that Mario Segety came up with, well, close to 20 years ago, now 15 years ago, a bit more. And what it does is essentially, it does the following. So you're given a classical walk with a stochastic matrix. And so what you're looking for is you're looking for a unitary quantum walk, meaning a unitary that is somehow related to that stochastic walk, which has the property that you know that one of the eigenvectors of the unitary happens to be sort of the purification of your fixed point of your classical random walk. I'll go through these things in more detail in a bit. And so that should be the one with phase 0 or eigenvalue 1 of the unitary. And the reason why you would do this is there's something called a quadratical gap amplification. So if your classical random walk so it had a gap delta, then the interesting thing is the unitary has what's called a phase gap. I mean, for unitary, everything sits on the unitary, the spectrum sits in the unit circle, but you basically have a phase gap that blows up by a square root speed up, which means for algorithmic purpose, you actually have quadratic improvements in the algorithms, and that's something you could care about. And the nice thing is you can massage this unitary and use it to prepare something that's called these quantum samples, which is these purifications of classical distributions. And there's various reasons in other quantum algorithms why you would like to have these purifications of classical distributions and have ways of preparing them in some way, or detecting them / reflecting about them. So to go into a bit more detail, so suppose what we consider here, you have like a discrete state space, and what you consider is an ergodic Markov chain on that discrete state space. You represent that by a column stochastic matrix. For now, really simple. You declare, you assume that since it's ergodic, aperiodic, let's say, you assume you have a unit. We assume we have a unique stationary distribution that is sort of full rank. And moduli is the fixed point of this, right? And as a crude approximation, you can look at now the spectral properties of that matrix, and you declare the spectral gap sort of between the first eigenvalue 1 and the next smallest one, the difference between them, and refer to that as the spectral gap. And at least asymptotically, in the finest sense, it's somewhat of a good metric of how fast you converge. There's certainly people here that know a lot more about these mixing times, convergence properties, and more advanced settings. But say for now, we'll just stick to the spectral gap setting. Okay, and so we assume, okay, so this is roughly asymptotically. This is what how fast you basically have to, how long it takes for you to converge to the initial distribution, given that you began with an arbitrary distribution in your evolution. So. And that's sort of like, typically in all these algorithms that use these Markov chains, this is roughly a way for you to estimate or bound the algorithmic complexity, how long it takes for you to prepare that distribution, sample from that distribution, and so forth. Okay, we assume that we're looking at a detailed balanced or reversible classical Markov process satisfying this detailed balance condition. And that will become important for this particular construction for these Segety walk operators, because they're sort of, they only work in this setting for when the chain is actually detailed balanced. Okay, and another thing we need is there's something called the discriminant matrix Q of the stochastic matrix, which is just a direct similarity transformation of the stochastic matrix with a diagonal matrix where you put the weight distribution of your fixed point on the diagonal. And it turns out that if P is detailed balanced, you can show that essentially Q becomes just a Hermitian matrix with your conventional Euclidean inner product. And so there's something nice if you calculate that out, if you write that down, and if you look at that discriminant matrix. A nice property of that discriminant matrix is, although you now left and right multiplied with a steady state distribution, the actual discriminant matrix in the end does not depend on explicitly on the steady state distribution. So you can just write it as the square root of pxy times square root of pyx, which is kind of an important thing if you want to use that to construct more fanciful unitaries in the end that shouldn't depend explicitly on pi. Okay. So what do we want to do? So what we care about is we want to come up with a unitary that that basically allows you to have a quantum sample with that's associated with this. So the general trick here is now basically in constructing the Segety unitary is that you double the state space, which we're going to talk about in a bit. And what the goal is going to be is you want to prepare something called or you want to detect, prepare, or reflect about a quantum sample, which is this particular state, which is essentially just the square root of all your distributions. So if you were to just measure one of those registers, the first x or the second x, you would sample x according to pi x, right? And it happens to be that by that similarity transformation, that happens to be the roughly the eigenvector, that happens to be the eigenvector of Q with eigenvalue 1 from left and right now, okay? So how do you construct the Segety walk? So there's a family of states that you can now write down. So as we said, what you have to do is you have to double the system. So you consider the two copies of the system at the same time. And then what you do is you write down a family of states, say tau x, which are defined as here. So it's x, and then you basically sum over all the, depending on whether you go left or right, all the sources / targets from your distribution. And so now you have basically for every element in one system, you have one of these states. The next thing you have to define is sort of a swap operation, which you can also see as a reflection, which is a swap between those two register systems. And you can define an isometry, which basically is an isometry from the double copied system into the set of states that you have there. Okay, once you've defined these three things with the Segety for your quantum walk, then you can check a couple of things. So one thing that the reason why you write them down, why you satisfy them is that you can actually view the quantum discriminant, the discriminant that you're writing there as basically just a projection out of the reflection that you've done before. Because you're acting now within isometry left-right, you pick out a particular subblock of the swap operator in a particular basis, and that happens to actually be exactly the discriminant matrix that you want to set up further. And now that you have a projection, now that you have an isometry and a swap operator, you can basically construct two reflections. So one reflection is the one that you had before, which is the swap operator. The second reflection that you have is a reflection about that subspace that is encoded in terms of this isometry. So and if you multiply those two reflections, you end up getting a rotation, which is a unitary. And this is going to be exactly the Segety walk unitary that we want to implement on a quantum computer later. And so the question is, so why do we want to do that? So what you can check basically is if you're originally starting out, what I said before, what you can verify is if you originally started out with a discriminant matrix Q that has a unique fixed point with eigenvalue 1, you can essentially observe that and verify that this square distribution, this quantum sample, actually ends up being also a vector, eigenvector with eigenvalue 1 of the Segety walk unitary. But then the interesting thing is, so there's something that happens as basically you get some spreading of that space gap that I mentioned before. So if you originally had the spectrum, lambda 1 through lambda n, say, and they were all your eigenvalues of the Markov chain, then you can show basically by working in the eigenbasis of your random walk that the phases of your unitary are just going to be e to the I plus 1 plus minus I arcus cosine of lambda j. And so if you now look at how far they're roughly separated, so if you a big task in a lot of quantum algorithms is that you have to distinguish certain phases or eigenvalues of different eigenvectors in that unitary, right? So which is what you are going to use the phase estimation routine to distinguish that. And the time by which you basically, that the algorithmic complexity, how long it takes you to basically distinguish between those, this scales roughly inversely with one of the phase gap. And so if you originally had now a random walk with a gap, say delta, what happens is that this phase gap basically gets now a square root of delta, so you get a spread out of the phase gap, and you get a quadratic improvement in that phase gap. So that's one way of getting polynomial algorithmic speedups for certain quantum type walk algorithms. Okay, so that said, this is the general setting that's been known for quite a while. This is what this is work that Segety has done. And now what we're trying to do is to do the same thing, but for Lindbladians. Okay, so our question is now the following. Suppose someone gives you a family of Lindbladians that satisfies some notion of detailed balance, which we're going to find soon. So then you know that they generate a Markov process as well, which has which has the same spectral properties as your classical random walk. Right now, suppose for now you drop now everything is sort of reversible, and you start dropping the unitary evolution from this, and then the question is, okay, given that Lindbladian, is there some way in which you could assign a unitary walk operator that has the same properties as the classical Segety walk operator has for classical Markov chains? Okay, and so okay, there's always a way to. You can always get your Steinspring dilatation from your Markov process and so forth, but that's not the type of unitary we're looking for. So we're looking for exactly a unitary that has all these properties, and the reason why we actually care about that is there are a lot of quantum algorithms that would care about preparing those Q samples. Right, so one reason is, okay, I want to just go and physically prepare Gibbs states quadratically faster than other quantum algorithms to do that for some physics simulation. That might be an application, but there are other applications that give you access to partition functions, estimating partition functions. If you have these Q samples, there are other applications that let you solve certain kinds of STPs faster. And so that's why we would care about finding a way or improvements in that area. Okay. Oops. All right. So what is the setting that we're considering here? So we're going to do the same thing as before, and let's assume we are looking at a semigroup that of TCP maps that is generated by some Lindbladian. Assume we are sort of in the primitive setting. You have a unique full rank fixed point that this thing converges to, and what you would want now is basically, okay, there's the spectral properties are similar, so the spectrum sits within the unit disk. If we later assume that it becomes reversible, you know that the spectrum is sort of in the interval +1, -1, and what happens is basically then the question is, okay, same argument. You can make it an asymptotic spectral gap argument of how long it takes you to actually converge to the steady state Gibbs state, the fixed point of that semigroup. And what we want is exactly now, is there some way of, if someone gives you, in our case, the generator, a way of basically coming up with the Segety unitary that has exactly those properties before, especially the spectral gap amplification that we talked about earlier. Okay. All right. So what we need is some notion of detailed balance, and what we found sort of practical to work with is I mean, there's many definitions, but there's a recent paper that kind of gives a nice insight into this. Is a paper by Carl and Maas, and they define detailed balance in terms of just the sigma GNS inner product, and that's sort of the definition we're going to be using. So the interesting thing is what they showed is if you can show that it is a sigma detailed balance with respect to this inner product, then a lot of other pretty much all the other inner products that you could define in the non-commutative setting, they become detailed balance with this as well. So we're just going to take that as our definition of detailed balance that we need to work with. Because the reason is what we will want, or what we want to exploit, is the fact that the generators that satisfy this sigma detailed balance property have a canonical form, right? And so what you can do is you can write this the generator of a detailed balanced sigma detailed balanced evolution in terms of the roughly in terms of the eigenvectors of the modular operator of that fixed point that you're looking at. So what you know is basically you have a certain structure theorem that tells you, oh, okay, you know that that the thing is a sigma detailed balance. You know that there's an operator basis of Lindbladians in which you can write this this generator, and these operator bases happen to be eigenvectors of the modular operator, as we say, and they have particular properties. So that's an orthonormal operator basis with respect to the trace inner product. They're all orthogonal to the identity, and there's a property that we will need explicitly later in the general case, and that is basically there's a way of associating by just Hermitian conjugation pairs of those eigenvectors of the modular operator, or basically Lindbladian expansion operators, and we need that basically this association from one going to the other to construct all our elements and see that they work out. So that's sort of the place where we start to sink our teeth in and show that you can construct all these isometries and so forth. Okay, right. So having that, you can let me go one back. So you can just in our case we just use define this this inner product in terms of some map gamma sigma, and you can just think about this as right multiplication by sigma. And if you for the simplest, you can choose other ones. You can choose the symmetric ones if you like, and so forth. But if you have that, what you can do is you can define, of course, a quantum discriminant, in which is basically you right multiply with this with gamma sigma, square root of gamma sigma, followed by the channel, then inverse gamma sigma, and declare that to be the quantum discriminant. And it turns out that exactly this matrix has it becomes Hermitian relative to the Hilbert-Schmidt inner product And so it's sort of exactly the same situation as you had classically. Trivially, P and Q have the same spectrum. And now what you have is, if you look at just the unique fixed point of sigma, or whatever the matrix, which is now not normalized anymore, that corresponds to the eigenvector 1, it's sort of the square root of your original density matrix, okay, which is a very analog situation to what you had classically before. Okay, what we want though is, in our case, as we want to consider the scenario where the semigroup is not given an integrated form, because that becomes a bit untractable for us. I'll tell you why in a bit. But so we assume that it's given sort of in this sigma detail balanced of form in this canonical representation, and we shall make an additional requirement. So what we want is that this generator itself sort of sits in the spectrum interval between +1 and -1 itself, right? So if it's a finite dimensional system, you can always force it to be that way. In the setting that we're going to consider with all these algorithms, you can make that happen as well by just renormalizing that. And then what we're going to do is we're going to define a slightly modified version of a quantum discriminant for the said Lindbladian, and that is we're just going to take care that 1 plus that similarity transformation of the Lindbladian. This is the one we're actually going to be working with. Okay, so then going forward, what you need is a very little trick that people should be probably all familiar with. Is, oh yes, you can just vectorize individual matrices. So you can do the following. So if you're given a matrix, you can just look at this in the column stacked form if you want it. Or you can basically associate just a different basis and write it just that way. The reason why we do it, I'll show in a bit, it's sort of a trivial thing that you can do. And you can basically view this as an isomorphism between the space of matrices and the space of the tensor product space between two copies of the original system, which happens to be exactly what we will need later on for our construction of the walk unitary. Okay, and so then there's some neat identities where you can say, okay, if I have left-right multiplication with some vector x, I can represent that basically with the vectorized version of x and having two tensor copies, A tensor B transpose acting on x hat, which is an identity we'll need a little bit and quite a bit. And then composition in an application of channels becomes then just simpler matrix multiplication on the tensorized copied space. Okay. So the nice thing is now, if you now look at the vectorized version of our fixed point, that happens to be exactly the state we would like to prepare, right? So if you look at tau hat, that is one purification of our original density matrix. So suppose you're given the original density matrix sigma as in terms of spectral decomposition. What you can immediately see is the eigenvector with eigenvalue 0 that corresponds to that quantum discriminant happens to be exactly the purification of our density matrix when we're looking at a said matrix version of the quantum discriminant. Okay, good. So what is it that we want now? Since we've done all this, where do we want to go with this? So in order to replicate what happens with classical Segety walks, and on a formal level, our task is, so if someone gives you a quantum map, a Lindbladian that is detail balanced L, and your job is now to basically go and to find an isometry T and a reflection R, so that this matrix that we now looked at basically happens to be just a submatrix of that reflection R in a particular basis. Once we have that, we can basically extend the entire framework that we know exists classically, because that is just basic linear algebra that all these properties hold, and so you don't really have to exploit anything particular fancy beyond that. And so that's referred, by the way, that trick is referred to as a block encoding. And it has exactly, and you can show basically all these block encodings lead to that type of the Segety walk behavior for that unitary of the reflection, meaning you have eigenvalue 1 as the purification, and you have a quadratically increased phase gap. Okay. So that's sort of what we'd like formally, but algorithmically what we would like is something a bit more. Given such a quantum map L, we would like to have an efficient quantum algorithm that implements that unitary and that reflection. Okay, and there's a lot of things that I'm not going to be talking about, and so I will be sweeping under the rug. In principle, what you can't, since you have finite resources and phase estimation, many other finite resources, you will not exactly implement that the unitary corresponding to the exact quantum map that you would like to implement. There are certain errors and perturbation that you have to take into account, finiteness of phase estimation being the most dominant one. But most of the work actually goes into formally showing that that's still fine, and you end up with something that is, in all senses, reasonably close to where you started from when you do that. But I'm just going to convey what the main idea is. But that's sort of the idea, roughly, is you want to have some approximation of that, of a unitary that basically, you want to have a unitary that approximates in some sense the corresponding quantum map with a closed fixed point, closed phase gap. And but the next thing we practically want is a similar property as we have classically. So what we would like to have is basically that the quantum discriminant that we constructed explicitly in the first step sort of depends on the fixed point. But what we'd like is that that property sort of drops out as well, and so that unitary that you want to implement in the end and the corresponding reflections, they don't essentially depend on explicitly having to know the fixed point, which is what it is that you want to prepare in the first place. Okay, so what we do is now we're just going to run through this in an idealized setting with perfect idealized phase estimation for Davies generators. And essentially what happens is, once you know what happens for Davies generators, it can be easily extended to all the other cases by certain submatrix encodings and other little tricks. But the basic idea is just it works for Davies generators. And then once that's set, that's kind of easy. So in that case, so what's your Davies generator? Suppose someone comes along and gives you Hamiltonian with a spectral composition and inverse temperature. We assume we can simulate the time evolution of that Hamiltonian to do the phase estimation that we will need. Then your goal is to basically come up with a Lindbladian said Davies generator that basically describes relaxation to that thermal Gibbs state. Okay, and so what you have is basically a rough picture is you have a bunch of Bohr frequencies, which are pairwise energy differences between the energies of the Hamiltonian. And for a fixed Bohr frequency, you define a Lindbladian, which basically takes out a submatrix of an Hermitian operator S and projects that out, basically all the transitions that are induced by S. In our case, to make life easier for now, is we're just going to declare S is going to be a reflection, meaning it's unitary and Hermitian, so fine. So it satisfies both criteria. It has a certain symmetry relationship with this S minus dagger, S minus omega is S omega dagger, which is basically the property that I alluded to earlier on that we need in general for the reversible or detailed balanced Lindbladians. And also has this, oh, there's a typo, e to the minus beta omega. It has a specific property that there's sort of that essentially what this means is that these S omegas are eigenvectors of the modular operator. That's written here. And then we assume there is a filter function that has this symmetry property. And that's essentially all that you need. And then if you cook that together, you have one version of the Davies generator in the special form that we're considering. And it looks like a Lindbladian and has all the properties that we wanted to have. Okay, so given that, how do we construct now our isometries, our reflection, and so forth? And what we do now is basically let's talk about how to construct what the right isometry is for starters. Okay, so what you see are two circuit diagrams, T0, T1. Let's ignore T1 for now. Let's just look at the circuit diagram for T1. That's for T0. And we need 4 registers. So we need 2 copies of a physical register. So system 1, system 2, these are CN copies. The frequency register is basically just the energy or the pointer register for the phase estimation that we're doing. And then we need a single qubit filter register, which is going to apply the the metropolis or whichever filter rotation you want to do. Okay, so so the filter register is a single qubit. Frequency register is sort of R qubits if you want to resolve Bohr frequencies up to precision 1/2 to the R, at the price of having to simulate the time evolution proportional to 2 to the R. And now you have these two registers. So to construct that isometry, we're just going to write it out in that thing. So first we're going to act on the system 2 and the frequency register with a standard forward phase estimation, which is in the ideal case is this unitary. So what it does is pi k are essentially projectors onto the eigenvalues energy subspaces labeled k if they're degenerate, and you're starting out. So typically you start at 0, but we have to do it more general. Suppose if you start out in a pointer register of value p, it basically shifts your pointer register exactly to the epsilon k energy. So this is not what an exact phase estimation does. It's a pedagogical approximation, but this is what you would like it to do, right? And that's one thing. The next thing is a filter rotation that basically, depending on what the your values of the Bohr frequency is, it basically applies this single qubit rotation under the assumptions that g omega is positive and between 0 and 1, which can make it so, right? And so if you do that, you basically construct the following isometry T0. You first do a phase estimation, then you apply the Hermitian and reflection S as the sort of the kick operator. Then you undo the phase estimation that you initially did on the same pair of registers, and that computes sort of the relative Bohr frequencies that you incur by basically having had that kick operator, and then you follow it by this conditional rotation. And so what you can do is now you can do the same thing on the second case, the T1 isometry. And what you do there is you just do it with everything but complex conjugate on the second subsystem, including the filter rotation. And what you can then do is you can basically combine them based on whether there's an additional adder register that basically gets them both in superposition. You start in the plus state and you get both of them. So the isometry that you've just generated basically is now 1/2 T0 tensor identity plus T1 tensor 1, right? And okay, so much for the isometry. The next thing that you need is your reflection, and in that reflection, basically, there's also two components. There's an F. And what this F element does is going to take the role of what the swap operator does. And what it does is basically it flips omega to minus omega. So it basically associates the Lindblad operator S omega with the one S minus omega. So with its Hermitian conjugate, and they basically get flipped around. And once that happens, once this is actually applied in the filter, you also swap the adder registers around. So. Right, and so that essentially is the reflection operator. And so what you can do in a quantum algorithm is now, of course, decompose that in more elementary gates by the assumption that you can do regular arithmetic with your quantum gates, and you can go and do time evolution by some approximation of the actual Hamiltonian. Okay, so now if you look at that, what do those two components of the isometries look like formally? So what you've written down now, this entire transformation is essentially T0 and T1 has basically on the first register S omega, tensor identity times, if you came in with 0, the omega register times the filter register rotated. And the same thing happens for T1, but now you basically have those two registers swapped, and which you can, of course, then combine to an additional isometry. And the reflection that you now define is basically in terms of either applying, not doing anything if that flip qubit is in 0, or applying the swap operator and the flip operator between those two, and then actually swapping the filter in the end. So what we have is that these flip operators, they take omega to -1. The bit flip x is exactly the flip from 0 to 1. And it dictates which way the metropolis filter is being rotated. So, and if you do that and multiply this out as the matrix, you end up with the following Q hat matrix. which happens to be exactly, if you come from the other end and do the entire math, happens to be the quantum discriminant that we actually want to write down in the first place. Okay, in said ideal setting. And so by that we know, okay, now we have our T's, we have our R's, which are algorithmically implemented in the ideal setting, and that basically now allows us to cook together what the Davies generator is in the what the Segety walk operator is in the end. So I think with that I'm probably done. Oops. I want to not stop sharing. So if you have questions, please please go ahead. Ask questions.
Any questions? That was very interesting. What about if you would go for a non-Markov stuff? Sometimes we need to keep the memory, right?
Right. Ooh. Whether there's a way of associating. So what is it that you would want in that setting then? Say you were going to have a non-Markovian evolution.
Yes.
And so have some. Sorry?
Because of COVID, I invented some model, okay?
Okay.
I didn't do anything about that, but the model is simple. You have essentially probabilistic cellular automaton, except that if somebody gets ill, the person stays ill for some time, so either dies or not. If he or she doesn't, then is resistant for some time. Okay. So I suppose one could realize that in the way that you have a basic system, you do the loop and you do something on the second input, or you control the time somehow locally. But still, the problem is that you need to consider a large N, capital N, right? How to deal with that?
Oh, a large being large but finite, or large and infinite?
Everything is finite.
Everything is fine. Okay. Yes. So do you know what your do you have are you sure you have a steady state distribution of that non-Markovian process, or?
I suppose this depends on the parameters, right? Of the time of being resistant, and what is the range of possible interactions and things like that, right?
Right. Yes. I mean, it's a good question. I don't think that would really require something more that goes really beyond so I mean, that's a classical process, right?
Yes, but you can do this magic with replacing the dissipative stuff by a unitary. But then you need to have some memory or a random process which acts on the interface on the when you may run the process on some unit intervals, and then you take the output and do something with the system in the second loop and continue that in some way, right?
Right. And so the properties you would be looking for is you'd also ask for some quadratic or polynomial generally speed up for convergence of that process, or
well, and the thing is that you have to run in parallel a lot of things, right? And that's what quantum computing in principle gives you, right? If you want to look on the large population where the range of interaction is relatively small, essentially you are running in parallel a lot of things, right?
Right. In superposition, or how do you mean? Right. Yeah.
Well, you could separate subsystems by the range of interaction. This is one wave which goes in parallel, and then you apply another one which connects the stuff in between. But this goes in parallel as well, right? So probably that would be excellent for quantum computing, right?
Yeah, there's subtle advantages. Yes, advantages tend to be subtle indeed. Yeah, it's true.
So how big is a quantum computer now?
The one that's publicly available are 65 noisy qubits.
Okay, great.
So 64, I think 64, yeah, I think 64, 65 noisy qubits.
So it's still a few order of magnitude we need, but it's
what you need for fault tolerance. Yes, it's still not at the it's not at the fault tolerance threshold size level. No.
Okay. Any questions, please? Okay, so thank you very much again. Thank you, both speakers. Excellent.
Thank you.
And we hope to see you again tomorrow.
Yes.
Almost in the morning in some places, but well, in Europe it won't be afternoon, so it's okay. And stay healthy and stay cool. Bye bye.
Thank you. Thank you.